So our goal is to prove angle 1 is congruent to angle 2. So usually we try to prove that triangles are congruent. And then by corresponding parts of congruent triangles are congruent, we can prove that the angles are congruent. So 1 and 2 are part of these triangles here. So I would want to prove that this triangle is congruent to this triangle. And I've drawn them out here if you like to do that. So GDF is over here and HFD is over there. And I would love to prove that these triangles are congruent. Remember, when I try to prove them congruent, I've got side, 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 angle, side. Anything except a donkey, basically, no angle, side, side, right? So we do angle, angle, side, angle, side, angle. So what they've given me is, this was given that E or GD is congruent to HF. So this guy was congruent to this guy, and we know when we split them that they actually shared this side, DF. So by a reflexive property, I know that's true. And so they didn't tell me anything about this side, bummer. But if I can prove that these angles are the same, this guy and this guy, I can prove the triangles are congruent by side, angle, side. So side, angle, side, that's my goal. I just need these angles. Well, they did give me another piece of info that this whole thing is, or no, not this whole thing, that, my bad, this little thing is congruent to this little thing, EG and GH. So we're like, oh, okay, I can prove that if these little bits are congruent, then these whole sides are going to be congruent, because if I add congruent pieces, I'll get congruent segments. And then if those sides are congruent, once I prove that this is congruent to that, then I have an isosceles triangle theorem that says if the sides are congruent, then these angles are congruent. So those big angles there will be congruent, and that is GDF there and HFD there. So that's my goal. Now, unfortunately, what we see here as being, well, like, duh, with these pieces being put together to make this, and this piece is putting together to make that, and therefore this being congruent to that, sometimes takes a few steps depending on what textbook you're using. Some allow you to use certain theorems and some don't, so I do it the most slow way you can, just to be safe. Sorry. So, here we go. All right. So our goal again is to prove it's true by side, angle, side, and we're going for this side, this angle, this side. So this side here, how did I start this thing? One of the sides we already have by reflexive, right? That's that df by the reflexive property of congruence. And the other side we already have because they told us the GD and HF. So this was our other side here, GD and HF. And so the angle part is the part that the rest of this stuff is talking about. So first I give my given that the little pieces are congruent. And then, this is the most annoying of all, by definition of congruence, I can take off the little hats of these and say that the measure of EG is congruent to EH and the measure of GD is equal to HF and EG is equal to EH. And it's kind of just a technicality thing because I want to use this segment addition postulate, and the segment addition postulate deals with regular equality and not congruence. So I have to take the hats off to be able to use this, and then I'll put the hats back on later. Annoying, but we'll do it. So then I have to say this, that if I put EG and GD together, I make GD, or ED, it's alphabet soup. And then if I put EH and HF together, I get EF, and that's called the segment addition postulate. And again, it works with equality, which is why I had to take the hats off. Okay, that's all well and good. And now I need to prove that those two, ED and EF, are congruent to each other. So I do this a little, there's a couple different ways you can do this, but they all involve the substitution property. So I step it through it this way. I said that since EH is equal to EG, right? I said that there. I can substitute that. And since HF is congruent equal to GD, I can substitute that. And so if that equals that, and that equals that, and that equals that, then EG plus GD equals EF. And then I get to say that since EG plus GD equals ED, I substituted EG plus GD with ED. All right. And that equals EF. So ED, EF. Alphabet soup. Again, by substitution property of equality. And then I put the hats back on. ED, put the hats back on, is congruent to EF by the definition of congruence. And now I'm able to say, since I know these are congruent, these legs are congruent, these angles are congruent, and that's called the Isosceles triangle theorem, or if legs of a triangle are congruent, then the base angles are congruent. I use a lot of shorthands because it's a lot to write. And so we have that, and now I have my angle, and that's what I wanted. So I have side, then angle, then side, angle, side, all there, all stated very explicitly, so that now I can say that my triangles are congruent, GDF and HFD, by side, angle, side, and therefore all the pieces are congruent. So angle 1 is congruent to angle 2 by CPCTC. Yay, we're done.